So I'm really honored to be able to present today and to talk about some results on the stabilization of systems of coupled PDEs and characterizing their ISS properties using Lyapunov function. So actually, there is my name on the slide, but this work has been done in collaboration with a lot of people that I will cite through the presentation. So I know that in these seminars, usually we are dealing with time delay system, but today I'm going to talk about PDE and hyperbolic PDEs. But as you know, there are strong connection between PDEs and time delay systems. So why do I like studying PDE and hyperbolic systems? It's because they naturally appear when you want to model systems of conservation or balance law. When you have the evolution of some conserved quantities in space and time with finite speed of propagation. So the most common example is a wave equation, where you can directly see this propagation phenomenon. This kind of equation or natural representation for a lot of industrial processes for which you have long distance, for instance, with pipeline, it's the case for drilling devices, or slow propagation speeds at the traffic networks, for instance. The kind of simplest example of the system of balance law is given by the following equation. So we have a system of scalar balance law, and it's a system I'm going to use a lot to present some generic concept that I can then extend. So basically you have for the one who are not familiar with this representation, you have two equations. The red one, which corresponds to the U state, is propagating from the left boundary located at x is equal to 0, to the right boundary located at x is equal to 1, with a speed of propagation which is given by lambda and may depend on space. Then you have the V state, the blue one, which is counter-propagating with a speed mu. These two states are coupled in the domain with the coefficient sigma, but also coupled at the boundary with q and rho. And finally, we will consider boundary actuation. So we will assume that one boundary of the system is actuated. This system may be unstable due to the in-domain coupling terms or the boundary couplings. If you have nonlinear system, as it's the case for traffic networks, for instance, when you linearize them around a given steady state, then you get this kind of equation. The same with Sylvenant equation, for instance. So for this system, usually hyperbolic PDEs do not exist in isolation, and you have interconnection, either with other PDEs. It can be the case, for instance, when you model the mechanical vibrations in drilling devices, you have different pipes, so interconnection of PDEs, or electric transmission networks, where you have interconnection of individual transmission lines. You can also have couplings with ODEs that can model actuator dynamics, load dynamics, or sensor dynamics. So currently I'm working a lot on interconnected system, but today I will mostly focus on elementary system, which means that one boundary will be completely actuated. And I want to emphasize that this system may be subject to disturbances or uncertainties, and so it might be crucial to characterize their ISS properties. And in this context, ISS Lyapunov functions are really useful to design advanced control strategies at, for instance, event trigger control strategies. So even if you know that your system is ISS, it is of specific interest to be able to get an explicit ISS Lyapunov function. So regarding network, just a word, because it's my hot topic, so I like talking about that. Some application of networks or that can be used to describe mechanical vibration in drilling devices, where you have interconnected PDEs with ODEs that can represent the bit-rock interaction, or can also represent the actuation dynamics, or microendoscopes, modeling of microendoscopes, so flexible structure where you have different PDEs and the actuator are located at some point. Well, these systems are much more complex because, for instance, for the drilling device, you have several subsystems, but you only act the one at the top, so they are under-actuated. However, the results we present can be extended to this kind of interconnected system. Okay, so in this talk, I will present some generic techniques for the stabilization of PDE systems. So these results are now well known, but since not all of you are familiar with the control of PDE, I would like to do a focus on the robust stabilization and show how the backstepping approach can be used to rewrite the system as a time delay equation, in particular as an integral difference equation, and propose a robustification procedure. Actually, this representation as a time delay system will be crucial when we will introduce appropriate ISS functionals. So that's why I want to spend time on this point. Then I will focus on the ISS Lyapunov functionals for 2x2 hyperbolic system and show, recall the well-known Lyapunov analysis, but then show how this tool can be used to design advanced control strategies as event trigger mechanism, gain scheduling, or machine learning approximation of backstepping gains. Then I will try to extend the results for vector systems and non-scalar system, so n times m hyperbolic system. And we'll see that it's easier to design the Lyapunov functional for the linear difference equation instead of working with a hyperbolic system. Then I will give some perspective for future research. In this presentation, I won't talk about observer. I will just focus on state feedback. I won't consider the presence of ODEs, even if most of the results can be extended for ODEs. And then I won't give technical backstepping proof. I don't guarantee you that there will not be any technical details, but no technical backstepping proof. Okay, so we will start with the simple system of two coupled scalar equations. So it's the same system as the one I presented before, which is actuated at the boundary. Except that I will consider that sigma plus plus and sigma minus minus terms are equal to 0, because you can always perform a change of coordinates to get rid of this term. So this kind of system is well known, well studied. You have stabilizing controller design in the literature, but I will use it as a toy example to introduce fundamental concepts that I will later extend to more complex systems. So basically, for this system, when you want to design a stabilizing controller, you can use the backstepping approach. So this is just a quick summary of the backstepping approach. You want to map your original system to a target system for which the analysis becomes simpler. To do so, you use a backstepping transformation, which is usually an integral transformation and a Volterra transformation of the second kind. Some recent contribution, in particular regarding contribution with under-actuated system, introduce Freedom transformation, but the advantage of the backstepping transformation is that it is always invertible, which is not the case for Freedom transformation, which means that the two systems, the initial system and what we call the target system, will have equivalent stability properties. So the limitation, or actually the difficulty of the approach, is that you need, in the meantime, to find an adequate target system, which means a target system for which the analysis is simpler. But you also need to prove the existence and invertibility of the backstepping transformation. And both problems are related. However, for the system we consider, the target system is quite simple. Basically, you can just choose a copy of the dynamics and get rid of the in-domain coupling terms. So these in-domain coupling terms have not completely disappeared. They actually have been moved at the actuated boundary, and then now takes the form of integral coupling terms. So your target system is now composed of two transport equations and a boundary condition where you have your integral coupling terms. The advantage of this target system is that now you can directly use your control input to kill the bad terms, so the integral ones that can destabilize the system. Okay. And so this is a way to design the controller. However, if you go a bit further, you can have a time delay representation of the system. More precisely, alpha and beta are transport equation, which means that you can express alpha tx as a delayed version of alpha t0 and beta tx as a delayed function of beta t1. All in all, you can express all the states alpha tx, beta tx as a delayed function of beta t1. And you get the following integral difference equation, which is that beta t1, when t is greater than the total transport time, verifies difference equation. So you have beta t1 that depends on pointwise delayed value of itself, but with an integral term, so distributed value of beta t1, which gives you an integral difference equation where you have the control law. So for this system, it is necessary to have rho q to be smaller than 1 to guarantee the possibility of designing a delay robust control law. Why? Because if rho q in modulus is greater than 1, it means that the principal part, so just the difference equation without the integral terms, we'll have an infinite number of zeros on the right half plane. And so it has been shown that if you have an infinite number of unstable zeros, you cannot delay robustly and so robustly stabilize your system. So from now on, we will assume that rho Q is smaller than 1, which is a kind of dissipativity condition. But it's a fair assumption because otherwise you cannot design a robust control law. Then it is important to emphasize that the two systems have equivalent stability properties. They are not strictly equivalent, but the stability properties, for instance, in the sense of the L2 norms, are equivalent, which means that you can use this IDE as a comparison system to design controllers or to perform analysis, and you will get the same stability properties for your original system. So instead of having a system with two PDEs, you just have one single equation. So you have a reduction of the dimension of your problem. Okay. So the control law, the natural control law that was proposed in 2012 by Kirstich, Coron, Vasquez, and Bastin was corresponding to a cancellation of all these terms. Basically, you just wanted to put a zero at this boundary so that you had a propagation of the zero and you had finite time convergence. So finite time stability is good. However, it may raise some robustness issue. In particular, if the terms rho Q are large enough, you may have some robustness issues. This is what I show with this plot. So you have the nominal controllers that guarantees finite time convergence. Now, if you had a small delay in the loop, you may have some instabilities. And these poor robustness margins is due to the cancellation of the reflection terms, so to the cancellation of the product rho Q. So you can understand it if you perform a Laplace analysis. So for instance, your in closed loop, your system in the Laplace domain rewrite like that. So if you consider a delay delta in your control law, so you're still considering a control law that compensates for everything, but now you add a small delay in the loop, you get the following characteristic equation. And so in this characteristic equation, you have two pointwise terms that are different. Before, when delta is equal to 0, they kill each other. But now, if delta is not equal to 0, but really small, instead of killing each other, they can add up. And so you may have these equations that has unstable roots. In particular, it's the case when rho Q in modulus is greater than 1/2, because you have the condition which is given, for instance, by Hale and Lenel is that rho Q in modulus plus rho Q in modulus must be smaller than 1. So obviously, in the simulation I showed you, I chose rho Q in modulus to be greater than 1/2. So that's why killing all the reflection can be a problem. Now, what are the solutions? The first one is just to cancel a part of the reflection. So you, instead of killing all this term, all the pointwise term, you just kill a part of it so that you do not have any problem, because the integral term is strictly proper, so vanishes at high frequencies, which means that you will have robustness properties for that. So you can kill just a part of the reflection with the term A, or you can also low-pass filter the control law. So the first solution is easy to implement, but the analysis can become involved. However, we will see that there are some advantages for the first option. Then the second option, we have shown with Florent Di Miglio and Federico Brebiesca-Argomedo that it is always possible to design an appropriate low-pass filter so that the control law becomes strictly proper and you have closed-loop stability. Having a strictly proper controller is interesting because it means that your closed-loop system will be robust to admissible additive, multiplicative, or left coprime factor perturbations. Moreover, it will be robust to delay and W stable. So these concepts obviously relate to the concept of strong stability developed for time delay system, and it can be used to show robustness with respect to parameter uncertainties. Its main advantage is that the robustness problem is dissociated from the stabilization problem. You first design a stabilizing controller, and then to guarantee robustness without changing the closed loop stability, you combine it with a well-tuned low-pass filter. Okay. So from now on, I will just consider the first version of the control law. I'm just going to kill a part of the reflection. So if I kill a part of the reflection, I kill all the integral terms, I get the following closed loop system, where I have two transport equations and boundary couplings, which are Q and rho tilde. So my backstepping controller is now defined like that. For this system, you can characterize its stability in the L2 norm using a Lyapunov function. So this Lyapunov function corresponds to the classical L2 norm, but you have some exponential weights. So you can find it in the book by Bastin and Coron. And if you take the derivative of this expression, you replace alpha t by the PDE, use integration by parts, you get v dot is equal to minus v times nu, where nu is this constant, plus two positive terms, two terms that depends on beta square and alpha square. So if you can choose this coefficient q square minus kappa and rho tilde square, etc., to be negative, you will get v dot smaller than minus mu v, which is what you want. And actually, under the assumption that rho tilde q is smaller than 1, which is always possible because you can always choose rho tilde to be such that rho tilde q is smaller than 1 due to the delay robustness condition, then you can choose kappa and nu such that these two conditions are verified, and you will get v dot is equal, in our case, it's not a minus, it's not equal, it's smaller than, but you can choose it to be an equal if you want, is equal to minus nu v, and so it gives you the exponential stability using the equivalence between the Lyapunov function and the L2 norm of alpha and beta, and then you can use the equivalence between the L2 norm of alpha beta and of uv due to the invertibility of the backstepping transformation. So, okay, so this is a nice Lyapunov function to characterize the stability of the closed loop system. Now, what if we have disturbances? So if you have disturbances, let's say you have some in-domain disturbances, D1, D2, and boundary disturbances at each boundary. So I don't really bother about the regularity condition here, just to give some insights. Okay, so you can still perform the backstepping transformation, and basically you will get the same kind of target system, except that now you will have some, the disturbances may have been modified due to the backstepping transform. So D1 actually may be a combination, big D1 may be a combination of small D1, small D2, and D3, for instance, using the backstepping transformation. But all in all, you still have this kind of transport equation, and you can still use the same Lyapunov function and perform the Lyapunov analysis, except that now you get additional terms due to this D3, D4, D1, D2 terms. If you use Young's inequality and other classical inequalities, you can still bound v dot by minus eta v, where eta is a constant, might not be equal to nu, plus a gamma 0, so a function of or a constant multiplied by all the disturbance term. And so you can rewrite the L2 norm of your system as a function of the exponential decay, so plus a term that depends on your disturbance, which corresponds to the kind of usual ISS estimate. So this equation is extremely useful, and actually this based on this Lyapunov analysis, several advanced control techniques have been developed. So I'm going to show you how this analysis can be done to guarantee, can be used to guarantee exponential stability for some advanced control strategies. The first one is event-triggered control strategy. So basically, the control and estimation strategy developed for the traffic program, among other for hyperbolic system, need to be implemented at some point into digital platforms. So to avoid unnecessary updates of the controller, you can use some periodic sampling or sampling on events. Basically, you have your control law, which is continuous controller, but you only want, you will keep it as a constant, except when it's necessary to update it to stabilize the system. And so this is the event-triggered mechanism. It gives you the time sequence when you are going to update your control input. So it's event-triggered mechanism, or a rigorous way of sampling and efficiently use your control action. You avoid unnecessary facilitation of your controller. However, you need to show the well-posedness, show the closed-loop stability, and show that you do not have the Zeno phenomena, which means that you have over a finite time interval, you have a finite number of samplings. And to do so, actually, you can use the backstepping approach I show you with the Lyapunov techniques. More precisely, if we go into the detail, your backstepping controller, let's assume that I don't kill any reflection terms, which I can because rho q is smaller than 1, is given like that. So it's an integral feedback of your distributed state. So this controller is time varying. And when you propose the event-triggered controller, you will just assume that U and V are constants between tk and tk plus 1, and they are set to their value at t is equal to tk. And so this new event-trigger controller is piecewise constant. So if you want to implement that, you need first to determine the event-triggered mechanism that form an increasing sequence, tk, so the sequence of triggering. And your controller, the event-triggered controller, can be rewritten as UBS, which is the time-continuous controller, plus a term which is the difference between this event-triggered controller and the backstepping controller. And now this term can be seen as a disturbance, dt. And so if we use the analysis we have done before, it corresponds to a disturbance on the right boundary condition. So you can still perform the Lyapunov analysis, and you get V dot to be smaller than minus eta V plus gamma 0 d squared. And so the event-triggered mechanism, so these techniques have been developed among others by Nicolas Espetia and a lot of his co-authors, but including, for instance, Mamadou Diagne, Miroslav Kastec, or Yathan Karafidis. You can design the sequence of events tk such that tk plus 1 is the smallest t, such that this condition, gamma 0 d squared, smaller than eta 0 v of t, is not satisfied anymore. Which means that you wouldn't have, if this condition is not satisfied, then your Lyapunov function does not decrease anymore, and so you want to avoid that. That's why you set this condition. So if my Lyapunov starts to function or start to increase, then I'm updating my controller again. Of course, you need to be sure that this sequence tk does not generate a Zeno phenomenon. So this can be technical to show, but if you have a look in the papers by Nicolas, for instance, you can show that it is lower bounded and that there is existence of the minimum dwell time. So the proof is technical. It's not the purpose of this presentation. I just wanted to show you how the ISS Lyapunov functional can be used to show the stability of the closed loop system. And moreover, this controller can be improved using a dynamic event trigger mechanism or even periodic event trigger control and event quantization implementation. But this is not the purpose of this talk. Okay. The second example is the gain scheduling controller. So now in this setting, the coefficient sigma plus and sigma minus are time varying. We assume they are time varying, but quite with some regularity. Basically, you have a kind of Lipschitz condition on this coefficient. So now you have a time varying system, and it has been possible to design a time varying backstepping controller. So this is a really nice work by Jean-Michel Coron and his co-author, where you have backstepping kernels which are now time varying. However, having a time varying controller can be time varying kernels can be problematic because it means that you need to update them at every time instance. So it can be numerically extremely computationally expensive. And so it can be hard to implement such a controller in real time. This is why we proposed, grounding on some results by Yathan Karafidis, we proposed with Nicolas Espetia an event-triggered gain scheduling controller. So now your controller depends on time, but your gains are only computed on events. So K, G, and LG are the backstepping kernels computed for sigma plus correspond to sigma plus at time TG, and the same for sigma minus. The sequence of events have been designed such that the closed loop system is exponentially stable. So it's computationally cheaper because the gains are only computed on events. But the question is, again, how do we find the sequence TK? So to design the gain scheduling mechanism, we did the same trick as the one for the event triggered. Basically, we just consider, we rewrote sigma plus Tx as sigma plus TGx, and the difference between sigma plus Tx minus sigma plus TGx. And so these two terms that appears in the U equation and the V equation are again seen as disturbances. So again, we can use our Lyapunov functional and verify that V dots satisfy something like that. So now, if we define our event-triggered gain scheduling such that this condition is verified, then it means that we can show that our Lyapunov function is decreasing. So the proof is a bit technical. You need an additional condition, but it can be. It relies on this strategy. Okay. Again, you can show that you do not have any Zeno phenomenon, and the proof is based on the regularity of the time varying coefficient. And you have a lot of nice perspective about dynamical event triggered mechanism, small gain event trigger mechanism, and also what about time varying velocities or boundary couplings. So time varying velocities are a bit tricky because you need to change the Lyapunov functional, and you do not have a lot of results for that, but technically it is still doable. Moreover, you can combine this strategy with the previous one to have an event trigger gain scheduled controller. Then the last example I would like to show you is on the approximation of backstepping gains using neural networks. So I know that Miroslav and Kirsty and these co-authors have worked a lot on this topic. So basically, in particular, when you want to deal with adaptive controller, you need to update or compute your gain quite frequently. So the idea is just to emulate the backstepping gains, or even in some situation, the whole controller, using machine learnings and deep net approximation. And so the question is, what is the consequence of an approximation of the kernels? So for instance, for the deep net approximation theorem, you know that it is always possible to approximate the kernel scan L by k hat, which is given by a neural network, such that the norm between the two is smaller than a given constant epsilon that you have chosen. So it's the advantage of using neural network is that it can give you the kernel equation, the kernels much faster than other approaches, once properly trained, of course. So again, your control law, if you use the approximated kernel k hat and L hat, you can write it as the previous control law, the one with k and L, plus a disturbance term that depends on the difference between k hat and k. Again, you can perform your Lyapunov analysis and bound the D square by some things that depend on V, because as you can see, D is kind of related to the L2 norm. D square can be related to the L2 norm of U and V. And so you have a constant time epsilon. So if you choose epsilon small enough, then you're good. So this approximation of your controller can give you a faster computation of the backstepping kernels. And the question is, can we go further approximating the control operator? So this has been done by Miroslav and his co-authors, but can we also approximate the observer operator? And this is much more difficult because you have a kind of unbounded problem in this case. Okay, so this concludes the three examples I wanted to show you to emphasize that having ISS Lyapunov functional for PDE system is interesting and can be used in a lot of applications to design advanced controller strategies or to improve the performance of your methods. But we did it just for a simple system of two equations. What if now we have a non-scalar systems of balance law? So you can see that this system looks much more complicated, but actually you have the U state, which is of dimension n. So this state, which is of dimension m. You have in-domain coupling matrices, the velocity matrices of denoted lambda plus and lambda minus, but it's just a vector extension of the previous system. For this system, if you apply the backstepping methodology, you cannot kill all the in-domain coupling terms, contrary to what we could do for the scalar systems. You still have some in-domain couplings that depends on beta T0 and beta T1. But again, you can still apply the method of characteristics and show that beta T1 verifies the following integral difference equation. So you still have pointwise delay term that depends on the boundary couplings and integral delay term, distributed delay terms that depends, among other, on your in-domain coupling terms. So all in all, the system rewrites like that. Z of t is equal to a delayed sum of ak zt minus tk plus an integral between 0 and 2 of n zt minus nu. Okay, so two systems of equivalent stability properties, but you still need the same necessary condition for delay robustness, which is the principal part of the system, so the one without the integral terms, must be exponentially stable. So this is a necessary condition for delay robustness. And it means basically that your open loop system without the sigma terms must be exponentially stable. So with this condition, it's easy to design a stabilizing controller because basically you just need to kill the integral terms as we did before. And so you are just at the end of the day, you have just the difference part, which is exponentially stable. So this is a stabilizing controller, for instance. Okay, so for this system, the question is, for this PDE system, can we have a Lyapunov functional as we had for the scalar one? So you had a lot of results for in the literature, and the theory of ISS and its relation with ISS coercive Lyapunov functional is well established for bounded or admissible operator. I refer you to the really nice survey by André and Christophe Prieur. But otherwise, fewer results exist. You have some strict Lyapunov functional, given, for instance, by Jean-Michel Coron, which are the kind of extension of the Lyapunov functional we had before with these exponential gains. However, this function require dissipative boundary condition. So they require a condition on the spectral radius of this matrix to be smaller than 1. But this condition is more restrictive than the necessary condition for delay robustness we have. So in the case of scalar equations, they are the same. But generally speaking, this one is more restrictive, which means that there are some cases for which we know that we can stabilize the system, but this Lyapunov functional does not work. Other results exist with ISS for system of balance law with other dissipative boundary condition, Lyapunov theorem for hyperbolic and parabolic PDEs. So I refer you to this book by Karafilis and Kirstich. And you have some converse Lyapunov results. Similarly, for IDs, because we know that PDEs can be rewritten as integral difference equation, you have necessary stability conditions expressed in terms of a Lyapunov functional. You have by a paper by Roche-en-Campos, Montier, Di Loreto. You have a Lyapunov characterization with difference operators, a paper by Pepe, and Lyapunov characterization of the asymptotic stability of some nonlinear difference delay equation. But you only have sufficient condition for ISS. And in most cases, you may have some converse Lyapunov results. So you know that your system will be ISS. You know that you will have a Lyapunov function, but you may not have this Lyapunov functional. And as we have seen, having the Lyapunov functional can be crucial for some techniques. So we decided with Delphine Bresch-Petri to work on the design of a Lyapunov functional for a linear integral difference equation. So basically for this equation, we want, where you have a disturbance, an input terms f of t, we wanted to establish explicit Lyapunov functionals. So here we will assume that the delay are ordered and some regularity assumption. So we can assume that tau m is the largest delay, which is not restrictive. You just need to change n by a kind of extension of n. And we will assume that the delay are rationally independent, which is possible performing a state extension, change of coordinates. Okay. So now, for this system, which is a difference equation we had previously, we know that if psi, for instance, let's say I choose this this space piecewise continuous function, then there exists a unique solution that will be piecewise continuous. So it's just an existence solution and uniqueness. So this class of equation has been well studied in the literature, in particular by Hale and Verduin-Lonel. And if you write the operator associated with this equation, you know that this operator D is stable, which means that the solution are asymptotically stable, if and only if the characteristic equation, which is this complex function, has all its roots in the left half plane, which means, and you can show that its equivalent actually have to have the roots to be smaller than a given minus delta, but also to have ISS results, which is given as follows. So you can show that you have, we are bounded by the norm of the initial condition with an exponential decay and the supremum of your function between 0 and t. So you already know that you have an ISS result. However, it does not give you the ISS Lyapunov functional. So moreover, for this kind of equation, as we showed, I showed it previously, you may not have stability continuity with respect to the delays. And so that's why they added this additional condition, which is basically this theorem is just a concept of strong stability, and it corresponds to our robustness condition. So it's just another way to verify this robustness condition. Okay, so now we want to have an ISS Lyapunov functional. We know that the system is ISS stable for the the piecewise continuous norm or the L2 norm. Actually, using a result of Carvalho, it does not change a lot to change the state space. And you already have this L infinity ISS or this L2 ISS. However, the question is how to choose an appropriate ISS Lyapunov function. Does there exist one converse Lyapunov theorem? Okay. So to answer this question, we need to introduce some concepts that you can find in the paper by Rocha Campos, Michael Di Loreto, and Sabine Mondier. And which is the first one is the Cauchy formula. So basically, you can rewrite the solution of your difference equation of a difference equation. So now from now on, I will just focus on the difference equation because with our controller we can kill the integral part. And so you can express the solution of the difference equation as a derivative of the fundamental matrix, which is a kind of copy of the dynamics. The matrix K is piecewise constant with a set of discontinuity points. Then you can, they designed the Lyapunov, quadratic Lyapunov functional, and they wanted basically this Lyapunov functional to verify something like that, which is the derivative, the Dini derivative is equal to minus Z transpose WZ. So integrating, they obtain this equation. And then since you know using the delay robustness condition that your differential equation is exponentially stable, you can take the limit when t goes to infinity, and you get V0 is equal to this. And if you express it using the Cauchy formula, you get the following a bit ugly expression, but that depends basically on the matrix K and on its derivative. So the expression is a bit ugly, but at least it exists. Now, you want to go a bit further, and to do so, you can re-express this V0 functional in terms of the Lyapunov matrix. So the Lyapunov matrix is just a matrix defined like that, which is well defined when your DDE system is exponentially stable, which is the case against under the proposed robustness condition. Then you have U prime, which we write like that, and all in all, you can rewrite this term here as the second derivative of U. At this point. So this V0 is not equivalent to the L2 norm. So it cannot be used to be your Lyapunov functional. However, you can slightly modify it to make it equivalent to the Lyapunov functional. Basically, you just add this term, a new integral, and you can show that V1 is greater than something that depends on the L2 norm. And actually, so I'm not going to explain the proof, but you can show the equivalence between V1 and the L2 norm of the system. So this was for just the difference equation. Now, let us consider the controller. We have killed the integral term, but we still have this disturbance term, f of t. And we want to see the effect of this f of t on the functionals v1. And to do so, first, we will consider the functional v0. So we take v0, which is defined like that. We have some properties for U prime, which is defined, can be related to the matrix K. And you can show actually that the matrix U prime is piecewise constant and the set of its discontinuity points is countable. Moreover, if the system is exponentially stable, which is the case, then the quantity, this quantity is finite. So this lemma can be used just to re-express V0 as delta U prime TC, but you know that you have a countable number of discontinuity points. And all in all, if you take the derivative, you will get the term you had before, minus Z, basically minus Z squared, and some terms that depends on F and on the discontinuity point of U prime. So delta U prime is just the jump of U prime at this discontinuity points. Okay, so The proof is technical. I'm not going to give it, but it relies on some nice properties satisfied by the matrix delta U prime that you can show, and they are given in the paper by Rocha Campos and Mondier and Di Loreto. Then, how can you deal with the extra terms? So you need to tackle this term, the red one. You need to show the equivalence with the L2 norm, what we did with the V1 function, and you need to get a strict Lyapunov function because it's what is useful for the analysis. So to get with the red term, you can add some terms in your Lyapunov functional with this form where bk is a suitable sequence. You can show the existence of this term. To obtain the equivalence with the L2 norm, you can use the same trick as before, and you add an integral term with b small enough. Then to get a strict Lyapunov functional, you need to include an exponential term in the integral and perform the analogous analysis. All in all, you get the following V1 functional, which is a bit complicated, but it is a strict Lyapunov functional for your system. Okay, so this gives you the following theorem. For the inhomogeneous system with input f of t, the following statements are equivalent. The solution of the homogeneous equation is exponentially L2 ISS with respect to f, if and only if there exists a quadratic function V1 such that you have this ISS condition, and V1 is equivalent to the L2 norm. Of course, you have the Lyapunov functional here. You know it's ISS. However, you can understand that there is still an extra step to really use this functional, to implement it. So this is still something on which we are working. It's how to compute this V1, because this V1 can be used to give you theoretical proof, no problem, because you know it exists. So you can still prove the existence of the event-triggered sequence, for instance, for the event-triggered mechanism. However, when we want to implement it, at some point, you need to compute this V1. And so this is still work under progress. So to summarize this presentation, I first focus on some results of the robust stabilization of hyperbolic system. Then I show the connection between a hyperbolic system and IDEs, integral difference equation. For scalar system, I show the whole Lyapunov functional can be used to characterize the L2 ISS, and for non-scalar system, we used it to show we showed the L2 ISS of linear difference equation. Having L2 ISS Lyapunov functional is of specific interest when you want to deal with advanced control strategies for this system. Now the question is, what if we do not kill all the integral term, we just kill a part of it? Because, for instance, the integral term may help you to stabilize the system. So you do not want to kill it. As it helps you to stabilize your system, you want to keep a part of it. But it means that you need to analyze and to find an ISS Lyapunov functional when you have this term. For the PDE part, it will mean that you keep some in-domain coupling terms in the system, but now you need to define an ISS functional. And there are results, for instance, the one developed by Coron, but they require some LMI's condition. Then we express the ISS Lyapunov functional for the IDE. But what about the PDE expression? What's the expression of your Lyapunov functional in the UV coordinates? So this is still an open question. What about the delay robustness analysis? Because Lyapunov functional, again, can be used to show some robustness for time-varying delay or stochastic delays. So these kind of problems have been considered, for instance, for time delay systems by Delphine Brèche-Pétry recently with one of her PhD students. Now, the last question, which is the one I like most because I'm working on that, is what about underactuated IDEs, which can arise when you have networks of PDEs. So now, instead of having U of t, you have B times U of t. So you can only act on some components of the Z states. And so far, we only have some results for specific structure of the matrix B. For instance, when you have a kind of cascade structure, so you have some strong structural requirements on the matrices A, K, N, and B. Okay, with that, I will conclude my presentation, and I will be really happy to answer your questions.